first we'll take a look at these problem statements and hypotheses and see what we think about that. What do we expect to happen? So once you read through procedures, it's experiment section, picture what's going to happen, that we're rolling a ball down a ramp and timing how long that takes at each meter interval. So these problem statements, what you're going to have to answer for the hypotheses, say what happens to the velocity of the ball as it travels down the ramp. So do you think it's getting faster? Do you think it's getting slower? Do you think it has a constant velocity? And the second, so you'd answer that there, what happens to the velocity? And then the second one, what happens to the acceleration? So right here, is it getting faster at a constant rate? Or is it getting faster? Is it having increasing acceleration? The data for the distance versus time. Starting at lap 1, that would be at 1 meter, the total time, so 1.13. Lap 2 is the second meter, total time, 1.94. So I'm going to copy this. I'm going to go over to my data table and copy this data down. So we're looking here. At 0 meters, the time is also 0, because that's when time hasn't started. We also haven't released our ball, or at the moment we're releasing the ball, that's the moment we're starting the timer. Then I'm copying down the rest of my data, the rest of my time from the actual timer. And what we're going to make then is a distance versus time graph. And what do we expect that to look like? If the ball is speeding up as it goes down the ramp, then what we should see is we should see the slope of the line here increasing. So that means it's getting steeper. So the way that we'd see it getting steeper, increasing, is we'd have a little bit of a curve there, even if it's slight. When we graph this and we want distance versus time, that means distance is our y variable and time is our x variable. So then we're going to go over to graphical analysis and graph this. Make sure you're clicking manual entry because we are manually entering this. I am going to rename the data set. This is going to be my, oops, I'm going to turn this around. This is going to be my distance versus time of the ball down the ramp. And then my x is time, measured in seconds, and the y is distance measured in meters. Don't forget 0, 0 is a data point. And then I'm going to start entering in the rest of my data. Okay, so here is my data graphed. I've got those points plotted there. I see that my distance, my y-axis is the distance, and the x-axis is the time, so I need to go down here and get my trend line. If I do apply curve fit, it immediately pulls up linear, and I can see that it's not a linear relationship, so I'm going to change it to quadratic. See how that better fits? I'll move that out of the way. See how that better fits that trend, that relationship between that data? We've got a slight bit of a curve. The other thing I can do then with this is if I want to know what the slope is at each one of these points, I can click in the lower left again and then toggle on tangent. And then when I toggle on tangent, I can click on each one of these points and it will tell me the slope at that point. It'll also pull up the tangent line, which says, hey, if it was that slope for the whole thing, this is what that straight line would look like. So the slope at 1 second is 1.12. At the next one, it's 1.35. At the next one, it's 1.55. At the next one, it's 1.66. So now I'm going to enter those numbers because each one of these slopes is the speed. Slope of a distance versus time graph is the speed. So when I look at the slope at each point, it's telling me what is the speed at that point. Then I'm going to enter that into the second data table. Okay, here's the data table. It's on the back. I'm going to transfer my time, and then I'm taking that velocity from those tangent slopes on the graph. So when I was at 0 seconds, I don't have a velocity at that point because it's not far enough along in my graph, so I'm going to ignore that part. But when it was 1.13, then my velocity was 1.12, and these numbers are coming from the time that I initially timed. These numbers are coming from the slope on the distance versus time graph. So now we have at each time, what was the velocity at that moment? And that's the information that the graph gave us. So the next one, it says create a new graph, and this time we're gonna make a velocity versus time graph. So when we see this, we're gonna see, is the velocity increasing at a constant rate? So we are gonna go ahead and start with a new graph. If you haven't yet, go ahead and screenshot the distance versus time graph, because now we're gonna make a velocity versus time graph. So I'm gonna do a new experiment. I'm not gonna save this one for now. Still manual entry. This time it's going to be time is still on the x-axis, measured in seconds. And the y-axis this time is the velocity. And this one's gonna be in meters per second since we measured our distance in meters and our time in seconds. So now when we do this, I'm gonna enter in my data. And then we're gonna see what this graph looks like. So when I put my trend line in there, this time we do have a linear relationship, and my data is not quite as nice, but overall it does fit that straight line. So when the velocity versus time graph forms a straight line like this, it's showing that velocity is increasing, but it's increasing at a constant rate. If it's increasing at a constant rate, then our acceleration is constant. It's a slope anywhere on this line. Oops. The slope anywhere on this line is going to be constant. So if the slope is constant, the acceleration is constant, because slope is rise over run. Our y, or change in y over change in x, our y is velocity, x is time. So if it's change in velocity over time, that's the acceleration. Then go and look at your conclusion questions and answer those.